Hi, and welcome back to our Chemistry Flipped Classroom. And we are beginning our new unit talking all about gases. So before we jump into the new stuff, let's just review what you already know about gases. So I'm sure that you've been learning about gases probably since elementary school, and there's a lot of things you could tell me about gases. You know that they have no defined volume, no defined shape, that they expand to fill their container, that they're fluids, that they have a lot of motion. So what we're going to attempt to do in this unit is to understand on a molecular level why those things are, why do they expand to fill their containers, why do they not have a given shape, and as well as being able to calculate some of their characteristics and use them to relate certain variables to each other. So let's go ahead and jump in. So for today, we're going to be talking about pressure, what it is, how it's measured. We're going to work on describing the random motion of those molecules and how those relate to movement of gases. So when we talk about pressure, this is something that you define in your normal life. You say, I'm under pressure, or we talk about the pressure that our teachers or our parents put on us. So what do we mean by pressure when we talk about gases? Probably not quite the same thing as the pressure that you're under in school, but might feel that way. So pressure is caused by the collisions of molecules with the walls of a container. And it is equal to a force divided by a unit of area. So just as our ballet dancer exerts the same force when she's on point as she does when she's flat-footed, but when she's up on point, she exerts that force over a smaller unit of area, and so there's a higher pressure. In the same way, when we have a quantity of gas and we force it into a smaller volume, it's going to exert more pressure. So how do we measure pressure? Well, the first device that was developed to measure atmospheric pressure was developed by Evangelista Torricelli during the 17th century. And it was called a barometer, which just comes from measuring weight. Baro means weight, and meter or meter means measure. So it is a device essentially for measuring the weight of air molecules. And so all barometers essentially work under the same principle, that the air pushes down on the open area and pushes up a column of some sort of a measuring material, usually mercury. At sea level, which is where we are, the atmosphere can support a column of mercury that's 760 millimeters high. So if atmospheric pressure is higher, there are more molecules pressing down on that surface, and so the column is going to be pushed higher. If we have a lower atmospheric pressure, there's less force pushing down, and so the column will be lower. That force, again, is created by the mass of the molecules of the air that are pressing down on the surface of the mercury. Air pressure is caused by essentially the column of air that is between us and the exosphere, the outer atmosphere. So we have a lot of different ways of measuring pressure. We have a lot of different units. The one we'll use most commonly in the chemistry classroom is the atmosphere, but you'll also hear me refer to millimeters of mercury and torr, which are the same thing. A millimeter of mercury is the pressure that supports a 1 millimeter column of mercury in a barometer. Torr is named for Torricelli. It is exactly the same as a millimeter of mercury. And then we have pascals, which are actually the SI pressure unit, but a pascal is actually a very small unit, and so very often we use kilopascals. So remember, the pressure is the force that is created by those collisions of the molecules with the walls of the container. So we measure gas pressure in one of these units. And as we move through this unit, we'll talk very often about standard temperature and pressure. And so when we talk about standard pressure is 1 atmosphere. The equivalent in kilopascals is 101.3. It's 14.7 psi or pounds per square inch, 760 millimeters of mercury or 760 torr. These values are all the same. So these can be used as conversion factors. These are also all ways of expressing standard pressure. So standard temperature is either 273 Kelvin or 0 degrees Celsius. So when we're at standard temperature and pressure, it's 0 degrees Celsius and 1 atmosphere, or 273 Kelvin and 760 millimeters of mercury. We have to have both in order to be at standard temperature and pressure. So let's just really quickly review the Kelvin scale, because everything we do in the gas unit, we will have to be in Kelvin units. So you remember that the size of the degrees in the Kelvin scale is the same as the size of the degrees in the Celsius scale. It's just that the 0 point is different. So the Kelvin scale starts at 0 Kelvin, which is absolute 0, which means that 273 Kelvin is the freezing point, or 0 degrees Celsius, or 32 degrees Fahrenheit. So the nice thing about Kelvin is the conversion is easy. You just take your Celsius temperature and add 273, or depending on your significant figures, 273.15. If you're in Kelvin and you want to convert to degrees Celsius, you simply subtract 273. But when we are doing gas law problems, the temperature has to be in Kelvin. Okay, so that's standard temperature and pressure. We understand what pressure is. Let's talk about kinetic molecular theory. And this is really what describes the behavior of gases. So kinetic molecular theory is based on the idea that all gases are in constant motion. And so kinetic molecular theory talks about that motion as sort of the foundation of the behavior of gases. So here are the things, just a quick reminder that we know about gases. They expand to fill their containers. They are fluid, meaning that they can flow. They have a very low density, very low, 1/1000th the density of the equivalent liquid or solid. That they are compressible, meaning we can crush them into smaller spaces, and that they do these things called effusing and diffusing. And we're going to talk about the difference between effusion and diffusion. So the kinetic molecular theory is a model that helps us to understand the behavior of gas molecules. It's important to understand when we talk about the kinetic molecular theory that it describes the behavior of what we call ideal gases. So just like everything else in chemistry, we're describing an ideal, and we know that reality differs from that slightly. It makes 5 major assumptions, and we're going to talk about those assumptions. And generally speaking, gases behave like ideal gases. They follow the tenets of the kinetic molecular theory if pressure is not very high and temperature is not very low. Just a reminder that standard temperature and pressure is 0 degrees Celsius. So 0 degrees is not considered very low, okay? We're talking about temperature being very low would be well below 0 Celsius. So what are these 5 tenets of the kinetic molecular theory? First one is that particles of matter are always in motion. And we know that this is true. The only time that particles of matter are not in motion is when we are at 0 Kelvin. The other assumption, the next assumption of kinetic molecular theory is that the volume of the individual particles is approximately 0. This does not mean that the volume of a gas is zero. What this is saying is that because gases are so not dense, because they have such low density, that there's much more space in between the particles than there are particles. And so as they are relative to the volume that they occupy, the volume of the individual particles is so tiny that we can assume that it's approximately zero. The third major assumption of the kinetic molecular theory is that the collisions of particles are elastic. And what that means is that when the particles collide with one another or with the walls of the container, that all of their energy is retained. They don't lose any energy when they collide with each other or with the walls of the container. And as part of that tenet, we also say that the collisions with the container walls cause the pressure exerted by the gas. Fourth assumption is that the particles exert no forces on each other. Because they are so far apart from one another, those attractive or repulsive forces are insignificant. And the fifth tenet of the kinetic molecular theory is that the average kinetic energy is directly proportional to the Kelvin temperature of a gas. So let's explore that last one just a little bit. So at the same temperature, all gases have the same average kinetic energy. And the formula for kinetic energy is kinetic energy equals 1/2 the mass times the velocity squared. So what that means is that if you have two gases at the same temperature, the smaller molecules are going to have a smaller mass, which means they're going to have a higher velocity. Larger particles will have a larger mass, which means they'll have a lower velocity. So at the same temperature, because all gases have the same average kinetic energy at the same temperature, small molecules are going to be moving faster than large molecules. It's important to recognize that we're saying all gases have the same average kinetic energy. Are there going to be some particles that are moving faster and some that are moving slower? Absolutely. But on average, those particles will have the same kinetic energy. Okay, so let's talk about some of those characteristics of gases and think about how those relate to this kinetic molecular theory. The fact that they expand to fill their containers, it comes from that random movement of gas molecules. If you have a container, like we have in the top image here, where the gas is occupying 1/2 of the container, and we remove the wall, the gas is going to spread out, it's going to expand, and it's going to fill the container. And that's because those gas molecules are in constant motion. So if you remove the barrier, they're going to move to fill that space. In addition, if you did the same thing with a solid, it's not going to expand. And that's because the particles in a solid are attracted to each other. They're held in place by something called intermolecular forces. And so the lack of attraction between gas molecules is also a key component of this characteristic of expansion. Okay, fluidity. Why do gases flow? Well, in part because they're not strongly attracted to one another. And so as you pour them, they can move past one another, slide past one another without attraction for each other. So that's why we have fluidity, one of our characteristics of the kinetic molecular theory. All right, diffusion. So diffusion is the idea that if there is no barrier, that gases will mix. And this is what's responsible for the fact that you can smell things from far away. So when you walk down the hallway to the science and you say, "Ooh, they're doing dissections in biology," you can tell that when you walk in the front door of the building, because the smell is carried by gases and those mix down the hallway. Diffusion occurs because of that random movement of gas molecules, much like expansion. As temperature increases and movement increases, diffusion increases. Effusion refers to that movement if we have a small hole. So effusion is when gas molecules move through a small hole. So it relies on the same principles as diffusion, but it is slightly different. So diffusion is open mixing. Effusion is the rate of movement through a small type pinhole type hole. Okay, small molecules are going to diffuse faster than large molecules because they're moving faster than large molecules. And so we actually have this law called Graham's Law of Diffusion that says that the distance traveled by the gas 1 divided by the distance traveled by gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. Notice that it's an inverse relationship. So the smaller gas is going to travel farther than the larger gas because it's proportional to their speeds. And that finishes our introduction to gases, to the kinetic molecular theory. As always, I look forward to hearing your questions, and I'll see you in class.